Hello everyone, I'm going to talk about stochastic weighted matchings. This is a joint work with Mahsa and Derakhshan. We are both at the University of Maryland. I'll start with the problem definition. We are given an edge-weighted graph G along with a parameter P between 0 and 1. And then a random subgraph GP of G is picked by the nature, which includes each edge of G independently with probability P. We call GP the realization of G. We are unaware of the realization GP, but what we can do is to non-adaptively query a subset of edges in G to see which one of these edges are realized. And the goal is to query few edges and at the same time find an approximate maximum weight matching of GP. So slightly more formally, the goal is to pick a sparse subgraph Q of G, which achieves a large approximation ratio defined to be the expected weight of the maximum realized matching, maximum weight realized matching in QP, the realized subset of edges in Q, over the expected maximum weight matching in graph GP. Okay, so in this notation, mu denotes the maximum weight of a matching in its input graph. Because this problem has many applications in, for example, kidney exchange, online labor markets, and online dating. This subgraph Q can also be used as a matching sparsifier, which basically maintains a large or heavy matchings under random edge failures. Okay, so pictorially, suppose that this is our graph, and this is a typical realization of G for P equals half. And this is our benchmark. This this red matching is maximum weight matching of GP. And on the other hand, suppose that this is our subgraph Q. This is a realization of Q, the subset of edges in Q that turn out to be realized in the realization GP. And this blue matching is a maximum weight matching of QP. So we would like to pick Q such that in addition to being a sparse, it maximizes the expected weight of the blue matching over the expected weight of the red matching, the benchmark. Let's see some algorithms for this problem. So the first algorithm is basically suppose that we pick all the edges in G. Suppose that we query all the edges. Well, of course, the approximation ratio of this algorithm is 1 because Q equals P here. But on the other hand, this subgraph Q is not a sparse. It could have up to n squared edges, omega n squared edges. Now consider a different algorithm. This time we pick a maximum weight matching of G and only query that matching. This algorithm this subgraph has maximum degree 1 because it's a matching. But on the other hand, the approximation ratio guaranteed by this subgraph is only P. Why? Because suppose that the graph is a clique. It's not hard to see that even if the graph is unweighted, in expectation, we have a near perfect matching realized. But if we query only one matching, only P fraction of the edges of this matching are going to be realized, leading to only a P approximate solution. Now let's consider a more interesting algorithm. This algorithm was introduced in 2015 by Blum et al. We start with graph G. We take a maximum weight matching M1 of G, then remove this M1 from G. On the remaining graph, we pick a maximum weight matching M2. Again, remove M2 as well from the remaining graph. And now on the graph remained, which excludes both the edges of M1 and M2, we pick another matching and continue so for parameter R number of rounds. And then at the end, we let Q be the union of all these edge disjoint matchings. This subgraph is going to be a sparse because so long as R is not too large, it has maximum degree only R. And on the other hand, for the approximation ratio, many different works provide a different analysis of this algorithm. So the state of the art in terms of the guarantee of the approximation ratio for weighted graphs is an EC18 paper in which we show that it guarantees a half minus epsilon approximation, where the epsilon should appear somewhere in R, the degree of the subgraph. And on the other hand, Blum et al. Already in their 2015 paper showed that even if the graph is unweighted, this algorithm does not guarantee a better than 0.83 approximation. Now consider a similar algorithm with a subtle difference. Now, again, we have a parameter R, which controls the maximum degree of the subgraph Q that we pick. But this time we take R different realizations of G independently from each other, G1 through GR. So basically in each of these realizations, each edge appears with probability P independently from the rest of the edges and the rest of the realizations. And at the end, we let Q be the union of the maximum weight matchings of these R realizations. Okay. So for this algorithm, this simple Monte Carlo algorithm, we again have the same guarantee on the sparsity. So long as R is a small, we have a sparse subgraph. In terms of the approximation ratio, in our Soheil 19 paper, we showed that if the graph is unweighted, this algorithm obtains a 0.65 approximation. And later in a Stoch 20 paper, we showed that the approximation ratio of this algorithm for unweighted graphs is actually 1 minus epsilon, but again, this epsilon will appear somewhere in R. But for weighted graphs, the best known bound, not only for this algorithm, but also for the stochastic weighted matching problem in general, is only slightly better than half. We proved this in, again, our Soheil 19 paper, where we introduced this Monte Carlo algorithm for the stochastic matching problem. So let me quickly overview the related work, the known bounds, and what is our contribution in this paper. Basically, for unweighted graphs, Blum et al. In 2015 obtained a half approximation by querying only a constant number of edges per vertex, so long as P and epsilon are constants. The approximation ratio improved over time, and now we have 1 minus epsilon approximate algorithms for this problem, by again querying only a subset of only a constant number of edges per vertex, so long as epsilon and P are constants. For weighted graphs, however, the earlier works required the number of queries dependent on the maximum weight W in the graph, or also the number of vertices in the graph. And this was done by Yoshida and Yamaguchi and Mahara in Soheil 18. And the approximation ratio they guaranteed was around half minus epsilon. Later in EC18, we proved that this dependence on W and N can be removed. So we can guarantee the same half approximation by querying a constant number of edges per vertex. And later in Soheil 19, we proved that this approximation ratio can also go a little bit beyond half approximation. But still, there's a big gap between unweighted graphs and weighted graphs. There we have a 1 minus epsilon approximation. Here we have slightly better than half approximation. This is a gap that we close in this work. We proved that a 1 minus epsilon approximation for weighted graphs can be achieved by querying a constant number of edges per vertex, so long as epsilon and P are constants. For the algorithm, we use the Monte Carlo algorithm, but combine it with a greedy algorithm that I will soon describe. It's also worth noting that the dependence of degree on both epsilon and P is necessary. So any subgraph guaranteeing a 1 minus epsilon approximation for the problem should query the number of edges that depends on both epsilon and P around each vertex. However, an important open problem is whether or not we can guarantee a 1 minus epsilon approximation by querying a polymonomer epsilon P queries edges per vertex. So in our result, this O notation hides some exponential dependence on epsilon or P. Okay. So in order to achieve this result, we face several challenges that I will try to summarize here. Basically, in the analysis of the Monte Carlo algorithm we discussed earlier, where we have R different realizations G1 through GR and pick a maximum weight matching of each. One challenge is that these realizations G1 through GR are basically part of the randomization of the algorithm, and all of them may be very different from the actual realization GP, on which we have to find a large matching or a heavy matching if the graph is weighted. In fact, if we pick any of these matchings, fix any of these matchings, say the maximum weight matching of graph GI, only p fraction of the edges in this matching are expected to be realized in the actual realization GP. So what we would have to do is to take all these matchings, all the p fraction of edges in each of one of them, and use all these realized edges of these matchings and combine them to construct a large matching. And this turns out to be tricky for several reasons. The first reason is Erusa similarity barrier, which was pointed out in the work of Asadi, Khanna, and Lee in 2016. I won't go through the details of this construction, but basically, it has a Erusa similarity gadget inside. These are graphs that are dense, and at the same time, their edge set can be partitioned into many edge disjoint induced matchings. And each one of these matchings is also of linear size, really large matchings. And now, if we put this gadget and in addition add some outer edges, and in addition to that, if we allow a slightly, if we generalize the model slightly and allow these outer edges to be realized with some correlation, then it turns out that it actually is impossible to go beyond 2/3 approximation. So this is not the stochastic matching model because we are adding correlated realizations. But with this slightly extended model, it becomes suddenly impossible to beat 2/3 approximation. And what this tells us is that if in our stochastic matching setting, we want to go beyond 2/3 approximation, we would have to use the fact that all edges around the vertex are realized independently. Because recall that in this setting, only one edge per vertex is realized in a correlated way. Okay. So this bound was first broken in our Stock 20 paper, where we gave a 1-epsilon approximation for unweighted graphs. And the key to it was a notion of vertex-independent matching lemma, which we generalized in this paper to weighted graphs. So for weighted graphs, what this lemma guarantees is as follows. Suppose that we have some graph G, some edge-weighted graph G, and let A be some arbitrary matching algorithm. This matching algorithm could be randomized. It could have any kind of dependencies, any kind of correlations in how it decides to put which one of the edges into the matching. We prove that for any such algorithm A, there is another algorithm for constructing a matching M on realization GP of G, such that it satisfies these three properties. The first property says that for any vertex V, the probability that it is matched in M, the matching constructed by our algorithm, is going to be roughly the same as the probability that this matching algorithm A matches this vertex if we run A on realization GP. The second property says that this matching M in expectation is going to have weight that's at least 1 - epsilon times the expected weight of the matching reported by algorithm A, again, run on realized subgraph GP. Well, these two properties are actually not hard to satisfy. We could basically just use algorithm A to report M on realization GP. However, what's interesting here is the third property. This algorithm A may have any dependencies in how it matches the vertices. However, we prove that this matching M can be constructed in a way that in addition to satisfying these marginal probabilities and also having a large weight, for any subset of vertices U1 through UK, such that any pair of these vertices have large graph theoretic distance to each other with respect to graph G, then whether or not these vertices are part of the matching or not are all going to be independent of each other. Okay. I won't have time to go through the proof of this lemma, but it's a major part of the paper. And to prove it, we design a distributed local algorithm and use that to control the correlation of edges and vertices appearing in the final maximum matching. And it's also, again, worth emphasizing that the hard part of the proof is that we are operating on a stochastic graph. If the graph was deterministic, this would have been much more easier. Okay, so let's go to the next challenge that we face. It's about low probability, high weight edges. Suppose that the graph is unweighted. By linearity of expectation, we basically know that the expected size of the maximum realized matching is sum of the probabilities of different edges appearing in this matching. Right? But if we have a weighted graph, again, linearity of expectation tells us that the expected weight of the maximum weight realized matching is sum of the probabilities of these edges appearing in the maximum weight matchings times their weight. So the difference here is the weight. And the challenge with this difference is that if the graph is unweighted and an edge E has a relatively small probability of appearing in the matching, then its contribution to the size of the match, the expected matching, is also small. But on the other hand, if the graph is weighted, an edge that has a small probability of appearing in a matching may still have a very large expected contribution to the weight of the maximum realized matching because its weight could be large. And this reason, this difference is precisely the reason why our approach in the Soheil 19 paper obtains a 0.65 approximation for unweighted graphs, whereas the guarantee we could give for weighted graphs was only slightly better than half. It's also precisely the reason that separations are known for weighted matchings and matchings in, for example, online graphs. To give more context about how this challenge appears in our work, it's useful to go over a crucial, non-crucial decomposition of the graph. So basically in the literature, it has been proved that if we partition the edge set of the graph into two subsets, the set of crucial edges, C, which includes edges which appear in the optimum solution, in the optimum matching, with probability larger than some threshold tau, and non-crucial edges which appear in the optimum maximum matching with probability smaller than tau, then this partitioning can be useful for several reasons. First, most of the crucial edges will appear in our subgraph Q that we query, so long as the Monte Carlo steps are large enough. So in each step of the Monte Carlo algorithm, each one of the crucial edges appear with probability at least tau. So if we repeat the Monte Carlo algorithm for say 1 over tau steps, or some large constant times 1 over tau, then the vast majority of the edges in C will appear in our subgraph Q. On the other hand, if the graph is unweighted, we can afford to ignore a subset of edges of the non-crucial edges, because again, so as we discussed earlier, if an edge is non-crucial, if it has a low probability of appearing in the matching, its contribution is also small. So we can simply ignore a subset of edges, and this is not going to cost us too much. However, for weighted graphs, even ignoring a small number of edges per vertex could be problematic if they have high weight, even though their probabilities may be small and they may be considered non-crucial. So in our solution, what we do is we combine, as we discussed earlier, the Monte Carlo algorithm with the greedy algorithm. And the main intuition behind this greedy algorithm is we pick greedily some of the high weight, low probability edges and add them to Q. Okay, a third challenge, which is slightly more technical than the other two, is lack of a sparsification lemma for weighted graphs. Basically, in a work of AKL from EC16, we know that from weighted graphs, we can assume without loss of generality that the expected size of the maximum realized matching is linear in N. There is some constant, some smaller than one constant, where the expected size of the matching is this constant times N at least. And this is useful because once we apply this lemma and we assume this, we can simply charge the failures in the following way. So if around some vertex, some random process fails with probability, say, epsilon, leaving this vertex unmatched, we can still guarantee a 1 minus epsilon approximation because the cost of these failures is at most epsilon n, and the matching is linear in n. On the other hand, however, for weighted graphs, we are not really concerned about the size of the matching, but rather its weight. So this lemma doesn't really make sense for weighted graphs. We can still guarantee that the size of the matching is large, but the benchmark is the weight of the matching. That's what we are comparing our matching against. And so this lemma does not exist for weighted graphs. And the high-level solution in our approach is that instead of charging the failures to the vertices, we charge them to the edges. So for each edge, we say that, okay, the probability that there is some failure around this edge, very roughly speaking, is small enough that the expected contribution of this edge is still large compared to the probability that it appears in the optimum solution. Okay, so we can now finally get to describe the algorithm. So in addition to the Monte Carlo algorithm we discussed earlier, we use the following greedy algorithm. The greedy algorithm starts with an empty subgraph P, and then repeats this loop as we show, for up to 1 over epsilon steps. So we first define delta to be the maximum degree in P, or if this maximum degree is 0, as is the case initially, we let delta to be 1. Okay. Then we pick a subset of edges in the graph that is not part of P yet. So in the graph in E minus P, we pick the edges that either have a large probability of appearing in the matching, and this threshold is dynamic, depends on the maximum degree of P in the previous step. Or if the endpoints of this edge E are close to each other, there's a short path going through the edges in P, connecting these endpoints of this edge. So under these two criteria, we add edges to a subgraph I. All of the edges of I belong to E minus P. So none of them belong to P already. So what we do is we look at I. If the contribution of edges in I to the expected weight of the optimum solution is it's more than epsilon fraction, we add all of the edges in I to P. And we also prove that the maximum degree in I is going to be a constant. It's not hard to see, dependent only on epsilon and P. And if the contribution of these edges is more than epsilon opt, we add them to P. Otherwise, we ignore all of these edges in I, both in the algorithm and in the analysis of the algorithm. And because their contribution is less than epsilon opt, we're fine, and we can still guarantee about minus epsilon approximation. Okay. And also the reason that this while loop does not repeat itself for more than 1 over epsilon is basically the fact that at every step we look at a fresh subset of edges in the graph, and if they constitute more than an epsilon fraction of opt, we add them to P. So this cannot happen for more than 1 over epsilon steps. Okay. Again, so the reason that this greedy algorithm picks only a constant degree subgraph is kind of easy to prove, but what is hard is the analysis of how the edges picked by the greedy algorithm can be combined with the edges picked by the Monte Carlo algorithm and guarantee a 1 minus epsilon approximation. Okay, so let me also give a very high-level outline of the analysis. So in our analysis, what we do is we first look only at the greedy edges. The edges picked by the greedy algorithm. We reveal only the realization of these edges in P. Again, P is the subset of edges picked by the greedy algorithm. And once we reveal the realization of the edges in P, we now use the weighted vertex-independent matching algorithm we discussed earlier on this graph, and construct a matching Z on the set of realized edges in P. again, this matching Z is picked by the vertex-independent matching lemma. So it satisfies all those nice properties we talked about earlier. In particular, the independence between which vertices are matched in this graph Z. And then once we have this matching Z on P, we commit all the edges of Z to be in our final matching M that we will construct on in the analysis. Okay. And then it's the turn for the rest of the edges picked by the Monte Carlo algorithm that were not picked by the greedy algorithm. So what we do is now some of these edges may be already, for some of these edges, their endpoints may already be matched by matching Z. So we throw away these edges because we already commit Z to the final output. Instead, the subset of edges remain whose both endpoints are left unmatched. And then what we do is we basically pick a maximum weight matching among the rest of the edges that also turn out to be realized and augment M with them. So basically, if this is our graph and these outside edges are, for example, those picked by the greedy algorithm, we first realize them, construct a matching on them using the vertex-independent lemma and commit all of them. So for example, these remaining edges that touch the matching Z picked by the greedy algorithm would be thrown away immediately. And on the rest, once we realize them, we pick a maximum weight matching and augment matching Z. And now we use in particular the independence property guaranteed by the vertex-independent matching lemma and use that to argue that apart from a few ignored edges in this subgraph in this subgraph picked by the Monte Carlo algorithm, the rest in expectation have the same contribution to our matching M than they have to the optimal matching. And so in overall, we get that our the weight of our matching is the same on all these edges. And on the other hand, these ignored edges would not constitute more than an epsilon fraction of the optimum solution, precisely because of the way the greedy algorithm picked the edges. These edges that were ignored would correspond to the subset A that the greedy algorithm would choose to ignore at the last step of the while loop. So combining these, we prove that overall, basically the stochastic weighted matching problem admits a 1 minus epsilon approximation by an algorithm that combines the Monte Carlo algorithm with a greedy algorithm and queries only a constant number of edges per vertex, so long as epsilon and P are constants. And again, as we discussed earlier, dependence on both epsilon and P is necessary to obtain a 1 minus epsilon approximation. However, an immediate open problem, which is a very interesting open problem in my opinion, is whether or not we can guarantee a 1 minus epsilon approximation by querying poly 1 over epsilon P edges per vertex. And our conjecture is that this should be correct, but we have no idea how to prove this, what the algorithm should be, or how to analyze it. And some other problems related to this setting have also been studied. For example, packing LPs, minimum spanning trees, shortest paths. It's also interesting to see what are the right trade-offs for other graph problems in the setting. And that's it. Thank you.